Hello, everyone, and welcome to Ethproof call 8B. This is technically our 10th call, and it's going to be on Poseidon alternatives. Let me quickly share my slides. Okay, so today's call is going to be 2.5 hours. It's the first time I schedule it as 2.5 hours. Usually we overrun. Last time we spent a whole 2.5 hours on Poseidon, and I think it's a very important topic, so good to spend time on it. If you're new to the call, we also have a corresponding community Telegram group. That's t.me/ethproofs_community, and there's also a QR code for you to join easily. So today, again, we're going to be focusing on alternatives to Poseidon. And in the rest of the year, we have 4 more calls tentatively scheduled. The next one being on formal verification. And lots of very exciting things are happening with formal verification. For example, EVM ASM, which we're going to hear about soon. And this is scheduled to happen on June 26th. So what I'll be doing is sending a poll in the Telegram group. If you'd like a calendar invite, just respond to the poll. So today's Ethproof call is going to be split into 3 parts. We're going to have a few quick updates that we should go through pretty quickly, but there's a few like really exciting stuff here going on. For example, we have Francesco and Nicholas, who are new faces. We also have some short talks on hash function security in general, with some exciting announcements. For example, the Athena consortium, and then we're going to go into the meat of today's call with a whole slew of different hash functions. So often here we have some of the designers of these hash functions who'll be able to, in some sense, pitch their hash function, talk about the performance, talk about the security, and how they may be relevant for the blockchain space. Okay, so without further ado, I would like to invite Farah to give us some updates on Ethproofs.
Share my screen. Okay, Ethproofs. Yeah, the real-time proving cohort is live and it's been running every week, every Sunday night since our last call. So this is a snapshot of this week's cohort. Some weeks we've had up to 3 provers make the cohort. I think the biggest issue right now is just teams going on and offline to upgrade, which is kind of a good sign. So they're maybe not hitting the liveness score, which is 95%, but typically we're hitting over 95% for sub 10-second proofs for teams that do become eligible. We have completed the first security sprint milestone, so 6 of 8 ZK VMs on Ethproofs have integrated into SoundCalc, which is great. We are actively working on milestone 2, which targets improved security at 100-bit provable and smaller proof sizes at 600 kilobytes. So ZK VMs are upgrading, which is really good to see. So OpenVM 2.0 has come out by Axiom, Pico 2.0 by Brevis, and Airbender's 100-bit version is on staging and will go live into production next week on Ethproofs. And then we have new ZK VMs that have onboarded since the last call too, which is great because they've already integrated into SoundCloud. So congrats to ZK DTVM by AntChain Open Labs and Venus by Sisic. Our on-prem proving initiative is underway. So teams are currently getting set up with their hardware. We have a new page of metrics that's ready when those teams start to prove everyone in 10 blocks. So just a reminder that the teams participating in that are Brevis, Matter Labs, Succinct, and Zisk. And then finally, our Ethproofs validator to monitor the health of the ZK attester implementation, which is pulling proofs from Ethproofs to validate mainnet, is out of the queue. You can track it here with the validator number. So we can now start to monitor the health of the changes that we make, which here you can see it kind of went offline when we're updating verifiers in the client. So yeah, you can track that, and we'll have more updates on that in the next call.
Amazing. Any questions for Farah on Ethproofs? Okay, it's amazing just to see the continual progress on this. Thank you so much, Farah, for the update. Next up, we have Yoichi on EVM ASM.
Yes, EVMSM is about the guest that runs on these GKVMs. And this project is looks like this. So we do have a RISC-V specification in Lean. We have most of the interesting parts of the EVM specified in Lean, and there are like multiple, there can be multiple specifications. And then, so we have Lean things, Lean specifications on top and bottom. So like the issue is just filling in the middle. And it's a simple assembly programming, no compiler is involved, plus some program logic for assemblies. So, and then everything is done by AI models and agents. The code is generated by AIs and proof also. And then this workflow has been fairly agent friendly. Um, so a single loop of like codecs can generate like 200 pull requests per day and something like that. So, and they can like make mistakes, but they can also repair their own mistakes quite autonomously. So this has been working pretty well. Um, I gathered some numbers. So far, 55 EVM instructions have been proven to match a specification that's not checked, but if it's 256-bit additions, then I mean there can be just one spec. There are like trickier specifications like signed divisions. What happens if like divide by negative one has some interesting behavior. Um, the code base is roughly 150 lines, and it takes 4 minutes to build, so it's still okay. Somebody has been cloning this repo a lot, like 300,000 clones. So I don't know who is doing it, but yeah, please talk to me, like if you are doing this. If you have that many computers, maybe you can contribute as well. Um, the progress, okay, has been like maybe by instruction counts like 8%. And then like there's some overhead as well, so maybe it will take 10 times, 30 times more commits. That's Claude Code's estimate today. My own estimate was like we are currently at 5% or something. So it's fairly aligned opinions. So that's the code base. It's something interesting, so please have a look. That's it.
Yoichi, we have a question. What are you using to manage the loop?
So the loop, so currently I have, so both Codex and Cloud Code have fairly recent features for looping things around, like it's called goal or slash loop. So I'm currently using these. I sometimes use Hermes agent when I have access to API keys. At the moment, this is not being used by today, but I was also using this as well. The loops and goal commands work pretty well.
Are you targeting RISC-V 64 or 32?
It's 64. I'm just asking, I was asking this question earlier, and I'm just, yeah, following what people say.
Very nice. And is it correct that you're now working on this full time?
The agents are working full time. I mean, I'm sometimes like, just looking on the phone, and I was in Rome like 2 days ago, and I'm in Portugal right now, so the situation hasn't changed much, and yeah, Mediterranean experiences. So yeah, if I get like more tokens, then I can sometimes probably get busier on the phone or like even on laptops. But at the moment, the bottleneck seems to be like amount of tokens that I can put in.
Hmm. I mean, for context, I believe we gave Yuichi 10K of tokens, and he burned through 5K over a few days. But yeah, we'll work to get you more tokens. And it's also great to hear the progress. When we were in Cannes, you estimated 1% of total progress. Now it's bumped to 5%/8%. And this is extremely relevant to the canonical guest effort. And I gave a talk about this in Cannes, and hopefully the recording should be up in a few days. Thank you so much,
Thank you.
Yoichi. Next up, we have Felix, who will talk about ZK DTVM, a new ZK VM. If not, we'll move on to Francesco, who'll talk about LeanDA.
Cool. Can you see my screen?
Yep.
Okay. So we have been working on LeanDA, which is essentially post-quantum proofs of Reed-Solomon codes using LeanVM. So the idea here is we essentially want to construct some proofs which are viable candidates for replacement of KZG in the DA protocol in Ethereum. So I'm just going to walk through a few of the constructions. So the first construction is essentially using RLC. So the general idea is that each of these rows can be considered a code word or a blob, which has been Reed-Solomon coded and extended. And we essentially Merkleize each blob and then combine the roots of the Merkle roots of each blob to derive a challenge. And we use this challenge in the RLC to construct a final, a single row. And then we do a low degree test on this row using Frye folding. So that gets us to around 364 kilobytes per second in terms of message prover throughput. The next construction is using the barycentric formula or formulation essentially. So the idea once again is to the difference here is that we input these blobs. By the way, they're input into the VM via non-determinism, but we do them in even and odd ordering. Once again, Merkleize them, derive a challenge, and then use this challenge to construct the barycentric coefficients. And then for each row, we do a check to ensure that they're low degree using this barycentric formula. So that gets us to around 950 kilobytes. This should be noted. It should be noted that this is on an M2 max. For an M4 max, we can expect around a 2x in throughput. So reports of 2 megabytes per second on an M4 max using this construction have been reported. And then this is one that I've been working on more recently, which is essentially using an out-of-domain evaluation. So the general idea is that we take blobs as a non-deterministic input to the VM. So once again, these are the Reed-Solomon codes. We hash exclusive the systematic component of each blob. And then we then use the we hash the hashes of we hash the blob hashes to derive a random evaluation point. We use this evaluation point to basically produce an out of domain row. And what's nice about this is the fact that it binds the columns. So you don't have to do any hashing over the columns. You have essentially this random evaluation point. And then finally you just run the low degree test on this out of domain row, and yeah, you also Merkleize it. So this is the object that would be used for column sampling in the DA protocol. Yeah, that's all from me. By the way, I will share these slides in the chat, and there's links to the circuit implementations if people want to explore and experiment. And if you have ideas, please do reach out, because this is still an active area of research.
Very, very cool. Thank you so much, Francesco. So for those who don't know Francesco, he's also known as Tal Lepton. He used to be, I guess, a grantee at the Ethereum Foundation, and now is full-time, and it's great to have him work on LeanDA. And from my perspective, these numbers are kind of promising enough that I think it's quite likely that Ethereum would go with LeanDA. Great. Next up, we have Nicholas, who will talk about Sphinx Plus aggregation with LeanVM.
Thank you, Justin. I'm currently, hi, I'm Nicholas. I'm a master's student in Imperial College London. I'm doing my master's thesis on Sphinx Plus aggregation with using hash-based snarks. And around November, October time, I initially looked at Cairo, playing around with implementations, performance, looking at different hash functions, looking at different parameter sets, playing around with grinding and target sums in Sphinx Plus, all that sort of fun stuff. And I got some early results, but around February, a few months ago, I ran into LeanVM, noticed how good the sort of Poseidon hashing throughput is. Saw that XMSS is already implemented and decided to have a go with Sphinx Plus. And I do have sort of not quite complete, but mostly the way there. Like an implementation. You can see here's the results I ran yesterday. I'm able to aggregate about 2,000 signatures very, very comfortably, half a megabyte proof and about throughput 40 signatures per second. But this is on a university computer. Emil, who's the main contributor behind LeanVM, has managed to show about 140 signatures per second throughput with the same circuit. And actually what's very interesting is that LeanVM, the overhead, the main cost is actually the bit decomposition within Sphinx and making sure that you traverse through Merkle trees correctly rather than the actual Poseidon hash calls themselves. On the way, domains like full proper domain separation that's defined, looking at as well the new NIST smaller parameter set that's been released recently, and also looking at recursion for smaller proof sizes. Yeah, thank you.
Amazing. And for context, Nicholas, I believe, is a master's student at Imperial College, doing his thesis on signature aggregation. I guess I have one quick question. Why did you move from Cairo, and I guess what was your experience there?
So Cairo, it was just too slow. I was able to show up like aggregation over like naive concatenation. I was able to like save on about 33% in terms of like the proof size was 33%, 66% that of like if you just concatenated each thing's signature. But it took quite a while, and was very expensive in terms of memory. And my guess from that is because of like the Cairo programming language it's a lot higher level than what LeanVM provides. So the sort of blow up in constraints because there's a lot of range checks which are being done which you don't control, and yeah, so that's why.
Okay, got it. Thank you so much, Nicholas. Okay, next up we have.
Sorry,
Go ahead.
Justin. This is Felix from Antron Open Lab. Sorry to be late.
No worries, Felix. Go ahead, please.
Okay, can I? Can you see my screen?
Yes.
Okay. Sorry everyone. Sorry to be late. I'm Felix from Antron Open Labs. Today, I will show our results on real-time proving on JKDT VM. JKDT VM is on A3 Ethproofs now, using 1590 GPUs. Based on the result of 3,000 continuous proofs from Monday and Tuesday, the average proving time is 3.41 seconds. 99% of the proving time is under 4.28 seconds. 90% of the proving time is under 4.27 seconds. All proving time is under 8.6 seconds. Since we used 16 GPUs, we have 16 provers. Each prover has 5 task queues, covering CPU and GPU tasks. All tasks are fully pipelined to maximize GPU utilization and throughput. JKDT VM is a GPU-native JKVM, which has 100-bit provable security under UDR's assumption and using RISC-V instruction set. The proving system is based on Soundtrack PIOP and Colabel field. The core innovation of JKDT VM is for the block executor. We use JDEC, which is our block executor based on EVM1 that uses Pippenger algorithm and batched Moco tree updates to reduce the running cycles. For the emulator and trace generation, we use an aggressive static binary translator to turn RISC-V opcode straight into machine code and a GPU-native trace generator to build traces in parallel. For the proving system, we use Uniscape in the tail to fully use the GPU cores, plus a fuse track for lookup protocol to speed up lookup performance in GPU. For GPU acceleration, we design a multi-GPU hierarchical pipeline that works by blocks and shards across GPUs to maximize resources use. For the roadmap, we will release a new version that the proof size is under 600 kilobytes this month, and we will open source the proving system and block executor in August, and release a new version with 128-bit provable security and 300 kilobytes proof size before September. Thank you.
Amazing. Thank you, Felix. 99% of blocks proven under 5 seconds is really, really amazing. That's a fantastic performance. I believe one of your innovations is the Pangolin PCS, which is a new polynomial commitment scheme. Can you tell us a little bit more about this PCS?
We will tell the detail about this PCS about a few days later in our blogs and our Twitter. You may can read these blogs later.
Excellent. Really looking forward to this, and also looking to the open sourcing in August. Check if there's any questions. Nope, I think we're good. Thank you so much, Felix. Okay, next up we have a whole section on hash security, and here there's like multiple initiatives going on. I guess I'd like to just kick things off with a couple of updates. The first one is that we have this idea called multi-hashing XMSS, which is where the validators, instead of having a single XMSS tree with a single hash function Poseidon, they would, for example, create 3 XMSS trees, one with some sort of fallback hash function, which could be Blake3, and then maybe another one with a more experimental hash function, such as a monolith. We haven't really decided on the hash functions, but the concept basically is that if Poseidon were to break, we would have defense in depth with another hash function. And the downside here is that we might have to switch to GPU proving for the signature aggregation as opposed to CPU proving. So we lose a bit of decentralization. It's not ideal, but it's much better than nothing. And we're also looking into binary field-based proof systems to see if the performance could be good enough even on CPU. Although, unfortunately, it seems that only the Intel CPUs provide the instructions that we would need for binary field high performance. The other initiative that I wanted to briefly mention is the SHA-4 idea. So I gave a talk at NIST just a few weeks ago I couldn't find the talk online, but I'm sure I'll find it and I'll share the link. But the basic idea is to try and pill NIST to do a new hash function competition for snark-friendly hash functions. And I'm kind of very pleased to report that the idea wasn't like completely dismissed out of the bat. There seemed to be some amount of interest from the NIST folks, and we're expecting to have a call with the broader NIST cryptography team. Just to set expectations is going to take a very long time even to start this competition. So we're looking at 2029 or later just to start the competition. And then that competition would probably last several years, maybe half a decade. But still, I think this is kind of the ultimate endgame, if you will, potentially for snark-friendly hash functions. Now, next up, there's a very exciting initiative called the Athena Consortium, which might be a stepping stone towards the SHA-4 competition. And I'd like to invite Francois to tell us more about that.
Hello, I hope you can see my screen. Otherwise, yell, wave your hands, etc. Hi, I'm Francois. I work at Maiden. So as we have noticed in conversations with folks in the cryptography field recently, there's a wide agreement that with the new research on skipping class on Poseidon 2, folks want to migrate away from Poseidon 2. But what we noticed is that there isn't a lot of agreement on what they want to migrate towards. It might be Poseidon 1, might be something in the rescue class of functions, might be something else entirely. And because Poseidon 2 is kind of one of the fastest practical hash functions that we have, any migration is going to look like a downgrade, which kind of incentivizes cryptographers to try tweaks to hash functions that might help manage the downgrade in performance. I know that we just mentioned that we need a SHA-4 because Poseidon 2 itself might not be performant enough, but now imagine a downgrade from Poseidon 2, and that's going to be even worse. However, one of the risks of this is that those conversations are occurring with folks that, for all their qualities, and I insist, like all the industrial cryptographers that I've talked to are clearly very good at their job. They haven't dedicated 6 or 7 years of their careers specifically to symmetric cryptography and algebra-oriented hash functions. So who knows? They might do something safe, but they might as well also do something slightly unsafe. And those conversations are also siloed. So one of the risks is that we might end up with a field working in ZK in the next year that might make 7, 8 different choices in the matter of replacing Poseidon 2 with something. So everybody agrees we want to replace Poseidon 2. Not everybody agrees what we want to replace it with, and we want to avoid security breaks, and we want to avoid fragmentation. What to do about this? Well, we have figured out that a long time ago, Starkware had asked academic cryptographers to give concrete industrial guidance on which functions to use in this industrial context to do, say, a ZKVM or a ZKL2. That was all the way back in 2019, and that was kind of successful in terms of giving us more ideas around the security bounds and advancing the research on those hash functions. So we've asked the industry if they wanted to help with this community problem. It's been an honor, as far as I'm concerned, to witness the level of contributions that we've seen across the industry for cryptography as a public good. So we've managed to garner a little bit of a budget. And then we have a consortium of academic specialists, world-class folks that are working specifically on algebra-oriented hash functions that are going to give us guidance on the question of both what are the actual risks represented by the recent attacks on Poseidon, but as well what is the best knowledge that we have for replacements of Poseidon 2. This is, from us in the industry, something that we're asking without being dogmatic about which hash function to look at. There isn't also a requirement for funding members of the committee to follow the exact recommendation. Really, what we want is a menu, a short list, telling us here are the dishes on the menu. If you want to replace Poseidon 2, you have options A, B, and C. Here is what we know as of their soundness without any tribal knowledge going beyond what is published right now. And then maybe we will, during those 6 months, so the initiative has already started, we will contribute to benchmarks to help with all of this. With that, I wanted to give a hand of applause to the initial funding members of this committee that are really contributing to cryptography as a public good, and that includes EF. If you are not on this slide and you think that cryptography as a public good is fantastic and you have a little bit of money burning a hole through your pocket, know that we're raising for a fixed budget. If we haven't talked to you, it's probably that we haven't had the time. We're kind of running this on a shoestring of ops team. So feel free to contact me, and I will be more than happy to point you out at how you can contribute and how you can have your logo on the next iteration of this slide. We would very much welcome the contributions. With that being said, thank you very much, and a big kudos to everybody who contributed here.
Thank you, Francois, and thank you so much for the initiative. I think it's a great one, and congrats for getting so many funders in the initial round. You mentioned benchmarking. If I recall correctly from our conversations, you were thinking of potentially using Plonky 3 as kind of a Schelling point for kind of apples to apples benchmarks. Is that correct?
Yeah, so this is the main reason why you haven't seen logos of Aztec or Alio in there, is mostly because we have focused this on folks that are initially using small fields. Because first, that simplifies the work of the committee, that gives them a more clear target. And the other advantage, which is really incidental, is that this is a place that has Plonky 3 as a lingua franca. Everybody knows what benchmarks in circuit or out of circuit, in circuit being the difficult part, on Plonky 3 look like. And so that is going to give us a very clear target to be able to compare our optimizations of those different hash functions, however the committee happens to choose them.
Perfect. I guess this is a great segue to Leo, who will give us a little bit more technical information about the Athena consortium.
Yeah. Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay. And do you see my screen or anything like that?
We can't see your screen. We can see your video.
No.
Okay, now we can see your screen.
Okay. That's good. So, okay. I'm assuming you can see my slides.
Yep.
So I will remain at a very high level for now, because the work hasn't gotten started yet. But as was said, I was tasked with gathering this consortium of cryptographers. So thank you for entrusting me with this. The way I see it, I'm trying to answer that question, which is on my screen. Someone is asking for which hash function to use for their ZK system, which operates on blocks of fp to the n for specific values of p and specific values of n. And that person is asking, what should I do? And is it okay to use Poseidon for these specific sets of parameters? It's an excellent question because there has been progress on the cryptanalysis of functions like Poseidon. So on these algebraic hash functions, arithmetization-oriented hash functions, however you want to call them. First, algebraic attacks have wreaked havoc in this whole area. So algebraic attacks are attacks that rely ultimately on solving a system of polynomial equations. And you have techniques like the free lunch or the resultants that have proved much, much, much more powerful than what was anticipated by the designers of these functions, including myself. Recently, and more specifically for Poseidon, there is this skipping class paper where essentially some cryptographers have found a very clever way of writing the equations that would occur in these polynomial system solving based attacks, and to write them in such a way that they are easier to solve, so such that the solving algorithm is more efficient, which is a problem because then it means that the function is even less secure. And this attack, this technique to skip rounds, was much more powerful than what was known to be possible. So they managed to skip 3 rounds, while the best state of the art before was 1 or 2. So that was a significant breakthrough. And another issue, which is not so much a hint of insecurity, it's a hint of poor understanding. The focus of academic cryptographers like myself so far, has been on the case where P is huge, so your prime is more than 200 bits. And then as a consequence, your number of elements, your number of coordinates in the blocks on which you operate is smaller than 4, which is not what we are interested in here. The prime is much smaller and the number of elements is much higher. And that changes a lot of things in terms of cryptanalysis. So all the results that were relevant in that context, the big P, small n, might not be relevant in the smaller p, bigger n regime of parameters. So we will work in 2 steps. First, we want to improve the understanding, and we will write a detailed state-of-the-art on the analysis of these hash functions with a focus on relevant parameters. And then we will write guidelines. So we'll, as François said, we will select a small number of hash functions that we consider to be safe, and we will write clear descriptions of them, like a light standardization effort type of thing. So these are the cryptographers that have been kind enough to agree to join us in this effort. I'm not going to read all their names. As you will see, they come from all over the place. That's on purpose. They have specific expertise that are also all over the place, which is also on purpose. So I'm sure we will manage to make some important progress in this area. I have decided to call this project Athena to stick with the Greek goddess trend for these hash functions, and you can expect to hear from us soon. We will keep you updated on our progress. With that, I thank you, and I'm happy to take questions.
Amazing. Thank you so much, Leo. I'm not sure we can see the slide. Oh, there we go. Perfect. This is the last slide. Yeah, and it was great meeting you in Rome, and I think you gave an excellent presentation at the hash function event. It's a shame that it was not recorded, but hopefully you'll give the same presentation somewhere else where it is recorded. Yeah, just for context, Leo is kind of widely regarded as like one of the best in the field of hash function cryptanalysis. So it's a great honor to have him lead this initiative. Thank you so much for accepting to do this.
My pleasure.
Okay, next up we have Giuseppe, who will talk about some bounties that he may have claimed or will be claiming in the future. Giuseppe, the floor is yours.
Yep. Hello everyone. So this will be a really quick update. Just want to share, as Justin was saying, that I just want to share with you. So that a few days ago we claimed the secret shoe bounty for Poseidon 1 plus linear layer over Koala Bear. With the 6 full rounds and the 8 partial rounds. And we are currently targeting also the next one with 2 partial rounds more. So we didn't publicly share the technique yet. That's because we observed something we didn't really expect, and we would like first to investigate the reasons, if there are deeper reasons that could explain this. But what I could share instead is that our techniques doesn't use resultants to solve the secret shoe problem. And overall, the attack for the claimed verified bounty, the first one, the 6-8 one, costed only $300 in GPU computing. And so if you want to know more, of course, we're working on a report that we will share soon, and we will describe the details of what we did. That's all, and thank you.
Amazing. So $300 spent. What was the bounty? Was it 10K or 15K?
10K, yeah.
10K. Okay, very nice. And is it correct that you're trying to get the kind of the next bounty, and you've been hiring, renting hundreds of GPUs?
Yeah, that's correct.
Okay.
That's correct.
Well, good luck with
so
that.
Yeah, actually, okay, I will tell also these little details. The next bounty somehow seems will cost around 3-4 times the first one, which is a bit less than 9 times because the degree really increases by 9 times. There are different reasons for that, or probably also optimizations that implemented, but yeah, it's in the range of a few thousand. Yeah.
Excellent. And it is also
Thank
great
you.
to meet you in Rome.
Of course.
Next up, let me check the questions. Yeah, we do have questions. For the parental regime on this slide, white states over small fields, that's maybe a question for Leo. Like n equals 8 and 12 with 64-bit fields, or n equals 16 or 24 with 32-bit fields, is a concern that Poseidon is fundamentally unsafe, or that the existing Poseidon security analysis does not give enough confidence for these parameters? I think it's the latter.
Yes. So on a deep level, we don't understand the behavior of algebraic attacks as well when we are trying to fix more values. So basically, when you run these attacks, these algebraic attacks, you are targeting some coordinates of the output of the permutation. And if you're trying to attack one, for instance, if your prime is huge, or if you are trying to attack 8 of them because your prime is small, it's not the same. So it's more of the latter that we don't understand as well. At the same time, these round skipping tricks also tend to get more powerful when the number of elements increases. So that is also something we understand less, but that's something that's a bit more worrying. That would be the summary of it.
Great. Actually, we do have another question. Which attack class is the limiting one here? Interpolation, Grobner resultant, invariant subspace, or something else?
So invariant subspace and skipping class are not really their own attack. It's a way to enhance an attack where you're going to write a system of polynomial equations. So when you write your system of equations, the solving step has a given complexity. But with round skipping tricks, what you do is you write a simpler system that you can then solve using different techniques. And this system is simpler than what would have happened if you did not skip the rounds. And essentially, the complexity of the solving step becomes the same as the complexity you would have had if you were attacking fewer rounds, hence the name. It's as if the rounds you have skipped didn't count. That's why we call them that. The way in practice so far we have been able to find round skipping tricks was by reasoning about invariant subspace type of structures. So classical symmetric crypto techniques. In the case of Poseidon, the best attacks. So what you do is that you're going to write your system of equation that you need to solve somehow, and you have some freedom as to how. So you can use resultants. Maybe you can use the basic pipeline of F5 FGLM. I wouldn't believe that it's something we need to worry about, but who knows? And you will write your system using these round skips. Yeah. But it's not two attacks. It's two aspects of the same attack.
Got it. Thank you, Leo. Next up, we have Manuel, who will talk about superhash.
Hi, everybody. Can you see
Hi,
my
Manuel. Not yet.
Let me see. Can you see my screen now?
Still not yet.
I think I'll have to get out and come back.
No worries. Okay, let's move on to Danny in the meantime. Danny, the floor is yours to talk about algebraic-oriented security.
Yeah. Hi. Let me try to share my screen also. So give me a sec. I will have to rejoin maybe. Because of I have to rejoin. Sorry, because of the macOS security. I've got to rejoin.
Okay, no worries. I guess we can just get cracking then with the meat of today's presentations, which is the alternative to Poseidon. So let's start with SHA-2 as a potential candidate alternative with owner.
Hi, Jason. Thank you. Let me try to share my screen.
And for context, Honor received a grant from the Ethereum Foundation, and he's now focusing on making Lean VM friendly to Bitcoin, which means using SHA-256.
See my screen now?
Yes, we can see it.
Okay, cool. So, in short, we added SHA-256 precompiled to Lean VM for Sphinx verification, Sphinx Plus verification. So this Sphinx Plus is a PQ safe and one of the candidates for future use. And let me show you some verification requirements. It means if Sphinx verification means we need to verify Sphinx signature on Lean VM. So in the left side, we have these parameter sets, and the right side, the number of hashes we have to do in the circuit. So it's a roughly estimate circuit, but I just rounded up to be, yeah. So this one is seems nice, but I think this have less set of signatures that signer can use. Also, signature signing time a bit. I think there's that trade-off. So also, let me give some introduction about Lean VM. It has very minimal instruction sets, say 4 of them. So it has 2 precompiles, Poseidon, extensive field operations, and it's a multilinear, it uses multilinear proof system and GK for memory. In the backend, we have VLPCS, and it also has a Python-like DSL. So you can see that VM in that library. Yeah. So if we want to add SHA-2 to this VM, we want to add as precompile. Also, we want to change VLPCS. It was before working with Poseidon hash function. Now we have to also want to make it SHA-256. I mark it with this precompiler because in circuit SHA-256 expensive, but on the other hand, with SHA-256, PCS becomes a bit faster. Yeah, we have some benchmarks. First of all, we have this SHA-256 Air as PR in Plonky 3 from Toman. It's 700 cells in a single row for one compression. I made some benchmarks that uses Fry backend with Baby Bear Prime. For those input size, as you can see, it's 5 to the 10x slower than the Poseidon one. I mean, I want to share this as a baseline. Also, we have another SHA-256 Air implemented with lookups with STVO backend. it uses circle stack, and M31 prime. Its previous one doesn't involve any lookup, but was 7,000 cells, but this one has 4,000 cells. Then it's this difference is about lookups, right? And I think this tweet is related with this implementation, and they argue that they see 8 kilohertz on M2. I also tried to regenerate this result, but I guess I failed. I mean, not failed, I couldn't see that numbers on my M1 machine. But we also ported this SHA-256 air without lookups to the STVO library, this rookie numbers library. So I also compared two with lookup and without lookup on STVO. So lookups starts to pay off when input size getting higher. Input size means, I mean, number of hash, a number of SHA-256 compressed calls, right? It's I think yes, it starts to getting payoff when it's around 2 to the 15. Yeah. So also, I would like to share how lookups look like in SHA-256. They have a bunch of tables, 24 of them, and you can see the sizes of number of tables of these functions. These functions are in this SHA-256 algorithm. They include some rotations, shifts, XORs and adds. And we have such number of cells for this. I mean, this cells mean if you use lookup, these 7 million is the number of multiplicities we have to commit. And also, since there is no, it's a STVO, I guess it's not multilinear. So it's interestingly, these tables are has multilinear closed form. It means we don't have to send, I mean, prover don't have to send openings of these tables, right? I mean, if for a random point verifier can just calculate the openings of tables. If yes, all of these tables has multilinear closed form. Yeah. Lastly, we let me share with you our Poseidon precompile in LimVM. No, sorry, not Poseidon, SHA-256 precompile. In the left side, we see this. I also put this Poseidon timings to compare with the SHA-256. This actually in the second column is a SHA-256 precompile uses Poseidon backend. I mean, it's a vir, but it's in Poseidon. But in the third column, it's a SHA-256 with SHA-256 vir. So you can see the difference that there is some improvement when we switch to the SHA-256 vir. And also we added, we ported this rookie number air with lookups to the LimVM. I guess maybe it's not a very good implementation for now. It still didn't catch us the one with without lookups. I mean, these two are without lookups, and this is the one with lookup. So I guess, thank you.
Perfect. Thank you so much, Owner. I mean, the goal here is to try and have LeanVM be fast enough on the CPU to prove all Bitcoin signatures if they were all replaced with Sphinx Plus. With the new proposal from NIST, with 2 to the 24 messages that can be signed, that's 300 hashes per signature. Bitcoin does 10 signatures per second, so that's 3,000 hashes per second, and that's something that we should be able to do relatively easily. And the stretch goal would be to have the more expensive Sphinx Plus signatures, which I thought were 2,000 hashes per signature, but in your slides were 4,000. We have a couple of questions in the chat, but in the interest of time, Owner, can I ask you to answer them in the chat directly? And we'll move to Manuel to talk about Superhash. Perfect. We can see your screen now, Manuel.
Can you see the slides now?
Yes.
Hey, hi everybody. My name is Manuel from Lambda class. I'm going to talk about this idea that we had formerly known as superhash, in which we use techniques from equality saturation to design cryptographic hash function. So let me see if I can get it moving. The main idea here is that hash function can be thought of as a term that is like a composition of atomic operations, S boxes, linear layers, gate operations, and in that sense, terms are what E-graphs actually optimize. Our vocabulary so far is a very small one: S boxes, bit operations, and so on. And the good thing about this is that E-graphs and equality saturation work by rewriting designs. In this sense, a hash function is a design that we can identify with an invariant vector. This is somewhat of a fingerprint for the hash design. This fingerprint will talk about how resistant the design is, how it behaves in hardware, and so on. The idea being that if we think of a hash function as a term, we can actually rewrite it. Typical equality saturation deals with equality. That means if you have a design, you can apply rewrite rules to find equivalent designs. This means that you're going to find a different design which has the same security and performance properties. But the thing is that maybe we can improve a little bit and teach the graph to saturate a different kind of relation, which is not necessarily equality. So if we teach the graph to saturate directed relations, we can actually find improvements of the original design. Directed saturation will work with a criterion that is going to be stated in terms of the invariance that we are interested in. Maybe we want to have a design that's better behaved in terms of how resistant to linear attacks or differential attacks it is. We can also think of improving a design in terms of its performance and so on. The list of invariants that we are going to use is really up to now a convention. So this is really responsible for us at this point. The thing is that when we want to improve, we're going to be interested in having good ways of improvement. This is, we're going to have a different sorts of rewriting rules. Mainly handmade improvement rules made by cryptographers. For instance, if you add more rounds, or if you change parameters of the sponge block, these are going to be hand curated rewrite rules that they are going to be improving the original design. But also we can have a different egraph that it's not going to model the design of the hash function, but it's going to model a design of an attack for a specific function. In this sense, if we tie these two teams, these two egraphs, we're going to have this kind of loop in which one egraph will design and the other will attack. For now, we have like the foundations for this. All the equality saturation theorems we have in line already. We're going to work on the soundness of the directed improvements. We're also interested in having a larger vocabulary for this, having more atomic blocks to express more hashes. And we also have to work on closing the coevolution loop. That's going to be very interesting for us. At this point, we're optimistic. We have good reason to think that this will yield very nice results, and hopefully will become a good tool for cryptographers to use. So this is it for now. This is kind of a short talk, but if you're interested, just contact us and we'll gladly answer some questions. Thank you.
Thank you, Manuel. Next up, we have Danny, who will talk about AO security.
Can you hear me?
Yep.
Yeah. Okay, perfect. So hi everyone, sorry for the issue right before. So I'm gonna do a very quick intro about what's called AO-security. The name has to be changed, but it's an open wiki about arithmetization-oriented primitives. So let me. Oh, I cannot change the slides. Sorry, I am trying to switch to the next slide. Okay.
Yeah.
So sorry. So this it is a wiki that I started as a personal research initiative during a break to go deeper to the maths and the whole literature about arithmetization-oriented primitives. So we've seen many hash functions recently in the past few years. So it's Poseidon, Rescue, Griffin, all the other and many others primitive. So if the industry continued to rely on these primitives, we would need to keep track of all the research work and also see which actually blockchain or products in general use them. And on my side, during this break, I wanted to go back to the maths that are actually useful in these primitives. And I realized that all the security analysis, the algorithms, and mathematics in general are all scattered through, PhD thesis, GitHub issues, informal node, group discussions, videos like here also. But there is no single place to look it up. So I wanted to start creating a centralized and also a live reference for the crypto analysis of all the primitives using Lean4 and also Sage Code. I went through the Lean4 fever recently. Most of the content of the wiki, the link is at the end, is at the moment AI generated to go through the whole literature. And I also implemented some of the attacks from different papers that are available at the moment on existing primitives. And everything is gonna be available on the GitHub repo. Everything is open source. But so on the wiki, the idea is to list all the different primitives they designed, the security claims, list of all the published attacks, but also for anyone who is interested in the cryptanalysis itself, having like a kind of a course of all the cryptanalysis and the tools used for these primitives. And to go further, I wanted to initially the directions of the project is mostly implement in Lean or other theorem prover the lemmas, the theorems to verify actually if the pen and paper proofs are correct, and also track the open questions, because when you look at some papers, there are some open questions also, and having also an open source repository where in the same spirit as they exist for some elliptic curve cryptography primitives, to have a list of all the attacks. And also exploring independently some new directions that I've been talking with a few people, but also as I've heard from some people. So everything is open source at the moment. I mean, it's always going to be open source. You can go on the repo. Happy to move to any public good website or repo. So that's it for me. It's gonna be updated in the next few weeks or months. So it's gonna. I've got to go through the whole papers. That's it for me.
Amazing. Thank you so much. And I believe, Leo, last time you showed me some sort of a wiki as well that maybe one of your ex-students was working on.
Yes. Yeah, Danny, we should talk because there is my own. I'm with other people who are working on such a thing, and I was recently, as in half an hour ago, notified of another such effort. So we should get together, I think, because I think we all look at slightly different sides of this. But I agree with you that centralization would be the best. So yeah, drop me an email. We probably should talk, and then we can all contribute to this type of effort, because I think this type of effort is really welcome. As you pointed out, it's kind of a mess right now.
Totally agree with you, Leo.
Cool. Happy to connect you guys on Telegram if you're not already. Next up, we have we're going to be talking about Blake 3. So we have the Abednet team that's using it in production. Alex Vlasov will present, and we also have Alkindi from Maiden that has looked into using Blake 3 as well. So we're going to go through the hash functions sorted by age. So we started with SHA-2 and now Blake 3. Alex, the floor is yours.
Give me a second to share.
So in Ethereum, Blake 3 is probably a good candidate for every part of the L1, with one exception, which is the XMSS hashing, where we just have too many hash functions and we're doing the aggregation on CPU. But yeah, so for example, for the RISC-V ZKVM, Blake 3 could potentially work without any issues.
Okay, can you see everything? Can you hear me?
Yeah, we can see your screen, yes.
Fine. I hope to claw back a little bit of time so we can read it in parallel. It's also not Blake 3, but we actually use Blake 2. I will explain a little bit about the nuances. And I will only talk about it in basically conjunction with the Airbender as a RISC-V prover. Because we don't want to just prove Blake, we want to use it for something meaningful. Okay, so the motivation for Blake is simple. It's fast. I mean, arguably one of the fastest hashes for a CPU, at least. There are some nice internal properties, so native NDNS, but it's not that important. No need to maintain message expansion like for SHA. So, and it has internal structure, which is basically a loop. So instead of arithmetizing the full Blake hash invocation, like full round function, we can arithmetize internal permutation round. And as a nice properties, it doesn't require padding. So the node hashing is 2 to 1, exactly one round. And it's not inflated like each-active-56 with a huge internal state, which of course would require extra circuit variables. some internals of Airbender to have some context why it sells, such property sells important. So we have a very, very small set of circuits, less than 15. For recursion, we can't design anything. We just prove a recursion as a program. So, and in such program, we want to basically invoke the Blake. So that's why it's not just proving Blake, but it's a proving of the Blake together with some control flow attached to it. And from technical capabilities in Airbender, you can basically invoke a precompile at some moment in time over the global virtual machine state. So in the current version of the Airbender, currently used in Ethproofs version 2, so we only support a precompile, which is a single Blake to S permutation with additional options, which basically speed up the node compression. The circuit is the heaviest across all of ours in a sense of the width, basically number of elements in a row for typical invocation. But when we go closer and closer to the basically recursion root, so we just run recursion program over the one layer of proofs, and then we get some new proofs, we run recursion top of them, and we want it to converge to as little number of circuits as possible. So if we continue to use a Blake precompile circuit, individual circuit type, we have to prove it, and it adds to the proof sizes. So we plan to get in Airbender v3 next version, a more lightweight, even more internal primitive for Blake, which is internal quarter round function, how it's usually called in the paper, which is nicer to verify. So we need to pay less in recursion to verify it. So we can start to use it close to recursion tip. Also, one important thing to note is by default in settings, we use 7-round Blake in line with the parameterization from Blake 3 and the famous too much crypto paper. But it's not that really not that important. It's more like a historical reason, because most of the linear hashes which we have in the next version will be, I mean, all of them will be less than 1 kilobyte. So there is no difference between Blake 2 and Blake 3 in this mode. And there will be only one circuit where we'll require a little less than 2 kilobyte of linear hashes for Merkle tree leaves. And it's the only place where we'll actually pay for Blake 3 tree structure compared to Blake 2 linear hashing mode. So two concrete numbers. When we did the experiment, so right now our commitment scheme is Fry on Veer. I mean, most of the work is just a low degree extension, the creation of the Merkle tree. In this case, when we use Blake, it's 70% of time spent in entities or during the commitment, and 30% of the time spent on hashing. And when we experimented with the Poseidon 2, it was 20 to 80, so it basically flips the complexity of the commitment scheme, and it's dominated by the hashing in case of small fields. Commitment itself in the current version is 70% of the prover time, so this is unarguably a good trade-off. Don't have data for v3 yet, but eventually we'll get it. An important note, we only need to pay to prove Blake only when we invoke the recursion. So there is no Blake in the host program, at least in those we're interested in at the moment. So prover pays the cost to prove the Blake circuit only when the recursion is actually done. It's actually less work than the base program itself. And if we factor out all the prover cost per Ethereum block in our typical workload, then the prover only pays 30% of the total proving time to prove Blake related stuff. So with all the numbers above, it's just an arguably good trade-off for our case. Sorry, I was still out of time, but I tried to be quick.
Very cool. Thank you so much. Yeah, and the fact that you're only spending 30% of the time on recursion is really good. I'm curious, what is your 2-to-1 recursion
It's
time?
not on recursion. It's 30% on proving the Blake across basically the total prover work across initial guest program plus also recursion, which will happen.
Mm-hmm.
So
okay,
it's not that small. Yes, it's not that small, because the base layer is basically the guest program. It's the largest one in terms of number of RISC-V cycles being proven, but it's still good trade-off.
Cool. Al, do you have anything to add on Blake?
Yeah, not really, but so basically the question of Blake 2 or 3 boils down to the number of rounds. There's also the idea that Alex mentioned about using the permutation when you have like the 10 rounds, although I think he didn't explain more about it. So these are basically the things that we are still investigating. For Maiden in general, the key is not performance, but basically reducing the chances that we will need a hard fork or an upgrade in the future. Performance, like initial experiments show that for our use cases, it's not like a huge penalty. Maybe for recursion that might be, as Alex also showed in his presentation, but there are ways to go around it. Yeah, and security is basically either the defense for the 7 rounds, or one can also go with the 10 rounds. I think the delta between the two shouldn't be that huge. Just one thing that I would like to add is that if anybody's working on the same thing for Goldilocks, please reach out so that we can pool effort together. I think Zisk are looking into that as well. But if anybody else is interested, please reach out. Yeah, thank you.
Okay, cool. Next up, we have a hash function that I didn't know about. I think it was invented by Algorand. It's called SumHash 512, and we have Leo to talk about it. Do you have a Leo fan?
Hello, hi. Hey, can you hear me?
Leo. Yes.
Okay. Let me share my slides. So I'm here to talk about like SumHash, which is like adapted from AltaHash, and this work was done like several years ago when I was still at Algorand, and when I was at Algorand, like we do the quantum transfer, I think, at that time, and we choose several things that are key to this transition, and SumHash is one of them. So like the work has already been put into practice like for several years. So if you search like Go SumHash argument, the GitHub will pop up, and you can see all the details there. So it's basically like a subset SumHash function. At its core, its parameter has like 3 parameters, Q, N, and M. And the Q is homogeneous, the N is a dimension, and M is an imponence. And each function here is indexed by like this public well-known matrix A with like its n by m. And it takes a binary string of like length m, and then outputs are elements of integers modulo q. And
Leo, quick heads up. We can see your script, but not the slide itself.
Okay, sure. Sorry about that. Yeah, let me see how can. Yeah, ask my Claude to generate the script. Okay, so how about that?
Better.
So the output, that's and so it's basically a matrix vector multiplication there. And the conjecture security properties, like we have like several things here. So we have like collision resistant, target collision resistant, which also like imply a second pre-image pre-image thing, and then the one-wayness, and then the last one is on invertibility. So like if you put this thing like into some like the compression factor is like set appropriately, then you can have like this like collision resistance, which is equal to relax the invertibility. So which means like if you break like one of them, like you break all of them. And there's like one thing need to note that this like f sub a is like linear. It's not pseudo random, and of course it's not a random oracle. And please do not use that instantial one. Okay, so that's a construction, and then the cryptanalysis is like we use an idea of like called like merging tree. It's basically like a generalization of the idea invented by Wagner, I think, and then this idea was like proposed by, I'm not sure if I pronounce his name right. It's Shortenoff. Yeah. So like as you can see, like we have quantum. So like the estimation here is like the time plus memory, and we do it in favor of the adversary, where like the adversary is like doesn't cost anything to do sorting, or like the Grover search doesn't also cost anything there. So for here, this like argument is like some hash 512, where like the output length is like 512. It simply exceeds this like 128 bits of quantum security there. If you see the numbers in the table, and then the instantiation is to say like how we can instantiate this argument some hash. The first of all, as you can see, like the matrix A was like generated by Shake and using the state argument. Yeah, so like which means like we didn't build any backdoor in there. You can generate the A by yourself, and the outputs here is like N log Q, which is like 512 bits, and yeah, and here like we only like the original designs only handle fixed length inputs, but you can very well come to use like Merkle-Dahlgard training method to handle like arbitrary length with some stressing padding. And also there are like two modes, the sorting mode or unsorted mode. If you use sorting mode, then you have like pseudo randomness there. If unsorted mode, then it's like the plain sum hash. Yeah, so that's it. And yeah, you can search the GitHub for the spec and for the cryptanalysis there. We have both classical and quantum analysis for this like sum hash function. Okay.
Very nice. Thank you, Leo. Since this is, I guess, a variant of ITAI, it might make sense for Bini to present his presentation on ITAI hash functions now, and then we can take questions for the two of you simultaneously.
Yeah, thanks, Justin. Can everyone see the screen?
Yes.
Okay. Yeah, so yeah, it's kind of the predecessor of sum hash, and to be honest, I'm not a expert in symmetric hash functions, so please correct me if I say anything wrong. And this is actually a bit high level, and the motive is to encourage the community to explore about the snark friendliness about ITAI hash function. So I think this is most people already know this, so I'll be quick on these slides. So ITAI hash function was invented by ITAI 30 years ago, and the idea is really simple, it's just a matrix vector multiplication. So given a input, for simplicity, let's say this binary string, you just multiply a random matrix with it and get a smaller output. And initially, this is not very efficient. Actually, the rank of this matrix n is actually pretty large for security. But later we'll see a much more efficient variant. And the security of it can be reduced to SIS and then reduced to some worst case lies problem, and has endured like 30 years of cryptanalysis, and people believe for now is still secure against quantum computer. So as I mentioned, this is not very efficient. So in 2008, Lipshevsky, Michiancho, Piker, and Rosen introduced a variant of it called Swift hash function by leveraging the polynomial ring. So now instead of multiplying over ZQ and use a big matrix, you just do a inner product between a vector, RQ vector, and another random RQ vector. Essentially, this can be understood as a matrix multiplication, vector multiplication over ZQ as well, by equivalent considering this random vector as a negacyclic matrix. But thanks to the structure and the fast multiplication over polynomial rings, In fact, every input bit in amortization only needs to do about log n multiplication over ZQ. So it's much faster than before. For example, if n is 1000, now this is only 10. And additionally, the input norm can be slightly larger, rather than binary can be rather than can be a norm that has been bounded by some parameter. And the security of this can also be reduced to a variant of SIS, and people still believe that this is quantum secure. And for now, we don't have any better attacks correspond for this variant of SIS problem. And I have to say that the security parameter, the security level of the hash function is actually a pretty complex formula in terms of the parameter n, the rank matrix, and the modulus and norm of the inputs. And I would refer to this software, GitHub software called Lattice Estimator for the concrete number whenever you want to get a security level estimate. And this is based on all the best known attacks in these 30 years. And there are many more resources in that GitHub. So I really strongly encourage everyone interested to look at it. On the other hand, I also found that actually there is already a proof of concept of hash function over Goldilocks in two years ago by Zhenfei. And it's only a proof of concept. It's a very preliminary result. And the runtime and the snark circuit size is about 2 times larger than Poseidon. But I think this is only a preliminary result, and there are many spaces for further improvements. So I encourage engineer and researcher to look more to it. So finally, I want to highlight some nice properties about hash function and let's explain why it seems to be a good fit for snark friendliness. So first, it has very flexible choice for modulus. We only need this modulus to be slightly larger than input norm. So there are many choices for choosing it, such as a 32-bit prime. And another good to know fact is that this modulus Q doesn't have to be a prime. It can be anything, for example, power of 2. Even though I don't know how useful this will be in the snark setting, but I think it's a good to know fact. I want to highlight more about another property about hash function is somewhat linear homomorphism. So if you have some no-norm scalar C1, C2 and some no-norm vector V1, V2, then the linear combination of these two hashes is exactly the hash of the linear combination of the underlying vector. And this turns out to be very useful if you want to have more efficient snark proving, given this linear homomorphism. For example, suppose you want to prove correctness of multiple hash computation for some long vectors. And naively, you will just prove them separately if this is a standard hash function. But now if you have linear homomorphism, you can do much better. And the idea is to generate some randomness given this output hash output using some standard hash function that you can understand as a random oracle. And then you can encode this randomness as some no-norm scalars with in R in this ring. And then finally, you don't have to prove this separately. You just need to prove the hash once and prove that this linear combination of HI equals the hash of linear combination of underlying witness vectors. So approximately the snark circuit size can now be k times smaller than before, which is a great saving. And in particular, even better if this hash output are the public input rather than inside the circuit, the generation of the randomness doesn't have to be proved in the circuit. It can be done outside the circuit, so you don't even have to prove this standard hash function. But of course, if you have to, I don't think this is a big deal because this is only proving a much smaller input rather than a big input V1 to Vk. But I also want to mention there's some limitations. So I don't recommend to only using a hash function. So the hash output size is pretty large. Usually it's larger than 1 kilobytes, which is much larger than 32 bytes. So I would suggest that if you want to have snark-friendly hash function, but still small output, you should compose a hash function with another hash function that has smaller output size, so that you get the 1 kilobyte digest first and then compress again using another hash function. And some other care is that you have to make sure that inputs are no norm, but this is not very hard to just do some standard input decomposition. Okay, so I think that's basically it. The the key thing I want to convey is that ATI or the Swift hash function are pretty simple and is plausible post-quantum secure, and it has endured for almost 30 years of CRUD analysis. And it supports many different modulars, and it has a really nice property about linear homomorphism, which makes it a great fit if you want to prove hash computation for many and long input vectors. But I also want to warn that this is not the perfect panacea. Usually it has larger output size and some no-norm input requirements. So I would suggest if you want to use it, maybe combine it with another hash function with a smaller output size. That's it. Thank you so much.
Thank you, Bini. We have a question already. Are there any resources you can link regarding the linear homomorphism property?
Resource? You mean some?
I guess the original paper.
Original paper. I think this is kind of folklore. People, because it's matrix vector multiplication, so they have linearity. So it's a linear homomorphic.
Right.
Yeah.
Kev asks, since subset sum hash can be used heuristically as a random oracle, I guess this is a replacement for Peterson hashing in the post-quantum setting rather than a replacement for something like SHA or Blake. So for things like Merkle tree constructions, for example. Okay.
Yeah, it's basically only collision resistant. You cannot use it as a random oracle. But the Merkle tree can use collision resistant hash function as well. Yeah.
Right. I guess one question I have is, are you implementing a lattice-based scheme such as lattice fold, and do you have performance numbers that you can share for
yeah, unfortunately not for now.
Okay.
Yeah, but hopefully in the future. Yeah.
And do you know other teams that are implementing lattice-based SNOCs?
Yes, I know Netherminds, they have open source implementation. And there are several teams that are not open sourcing yet. But I think Nethermind is the one that have an open source implementation. And also, I think the team from EPFL, I think Alessandro's students, they have some library, right? Giacomo, do you know? Maybe Giacomo knows about this. I think there's another library that works, implement a lot of lattice cryptography. I forgot the name.
And is the Nevermind one Zinc Plus or something different?
It is a different library, but it implements many similar things, if I understand correctly.
Okay.
Yeah.
Cool.
I can try to find the link like later and put it on the chat.
Thank you. And Remco is saying that A16Z with Jolt has a lattice commitment implemented.
Right.
I believe they've implemented Hashi. Oh, there you go. That's the link. Yeah, perfect. Cool. Thank you so much, Binyi and Tom and Leo. Next up, we have Tomer, who will talk about Rescue Prime Optimized, also known as RPO. Tomer, you're muted.
Thanks. And now you can hear me, right?
Yeah, and we can see your screen.
Perfect. So yeah, Rescue Prime Optimized, which is kind of an instantiation of Rescue Prime. I think they're not that different. It's Rescue Prime with a chosen with one specific matrix. I'll talk about why it came to be. It's a work that we did in 2022 with Al, Willie, Alan, and Bobin, but then the original work on Rescue Prime was also with Simon, and before that on Rescue with Eli and Abdel, in addition to all these people. In the interest of brevity, background, motivation, some design decisions, state size and security, and a little bit of benchmarks. So I need to start from the marvelous design strategy. That is a generic way to create algebraic hash functions. And the trick in all those algebraic hash functions is to alternate between high degree and low degree power maps. And the trick to keep it efficient is that non-deterministic hinting allows to evaluate the high degree power map by folding it back, by having it as the compositional inverse of the low degree power map, and then you can write both S boxes at once as one low degree polynomial. So here in the picture, we can see that's one round of rescue, a 2019 paper. And the main problem here is that the high degree power map precedes the low degree power map. And what we saw is that when you fold it back, it spills over to the previous round. So in 2020, I think, with Rescue Prime, we swapped these two layers. So now the low degree power map comes first and the high degree power map comes later. And then in 2022, Bobin came and said that he needs a specific instance of this family to be used in Maiden to work on Goldilocks with 128-bit security and to be CPU efficient for client-side proving on edge devices. Now, to instantiate on Goldilocks and with 128-bit security is easy. That's exactly what the design template is meant to do. To do the client-side proving on edge devices required some optimizations. So these optimizations are only the least efficient part in all these functions is the 1/alpha power map, which is now in this figure is presented in the second part. But we can't play with that because that's it doesn't break the security, but we don't know what would be the security, or we didn't know. We know better now, but we didn't know what would be the security if we start removing high degree power maps. So we focused on finding an efficient MDS matrix. Eventually, we got. So this is a work that was done by Polygon Zero by Amish, and he found a circulant low Hamming weight matrix, MDS matrix to use. We put in some effort to verify that it's indeed an MDS, and when we convinced ourselves that it is, we used it as well. And we also made a small reorder of the operations within the round so that it would be MDS constant injection and the power map, and then again MDS constants and the power map, which is only semantics because MDS and constants are linear operations, so we can swap them and it doesn't affect security. In the RPO paper, we have two versions, one with 128-bit security with a 12-element state and one with 160-bit security with 16-element state, both of them with 7 rounds. And to the best of my knowledge, there is no known attacks today. So maybe it's time to consider to reduce number of rounds to 6 or maybe 5. And then, because I don't know anything about implementation, Al was kind enough to help me benchmark this. We see that for Goldilocks, RPO runs in 2.63 microseconds, whereas Poseidon 1 is 0.92. So about double, maybe even 3 times slower. But then for smaller fields, they're about the same. And this is expected because we know that the entire family of rescue functions becomes more efficient with a larger state size and with a smaller field, whereas Poseidon requires more rounds, which makes the circuit larger. That's all from me. I'll take questions.
Okay, great. Very nice surprise to see that you're matching the performance of Poseidon 1 with Baby Ben Koala Bear. I guess one question is, if we do reduce the number of rounds, does that kind of create fragmentation or confusion?
Well, I'm really a big fan. I joined Leo's project, and I think that's the right way to go. We should avoid this fragmentation. Yes, it could create that, but hopefully the Athena project will pseudo-standardize certain versions of these functions, and then we will all just converge to those. You could still make different decisions in your use case, but that won't make sense for you, especially if someone does recommend on 5 rounds. I'm pretty sure that people will start converging to the more efficient version.
Very nice. And I believe no one's using RPO right now in production. So I guess if we do the standardization beforehand, then there'll be less of a chance of fragmentation.
Yeah. Yes.
If I
Kevin's
may,
asking,
on the topic, sorry.
go ahead.
Yeah, just on the topic of fragmentation, I agree that fragmentation is annoying, but I think we can only really talk of fragmentation when the field is already kind of solidified. So like, yeah, Poseidon 1 has been around for a while and has been used by a lot of people. So making a Poseidon 1.5, that would be perhaps unwelcome fragmentation. But it's not the case of all primitives. And I don't know to what extent, like there is an interesting philosophical question here, if we should allow round numbers to be changed over time. But yeah, that's a question for another time, I guess.
Kevin's asking, how much of the performance degradation is coming from the inverse S-box?
The performance degradation of what? Like this is just the performance, like in compared to what? So sure, that's the bottleneck. If the question is what is the bottleneck, then the inverse S-box is definitely the bottleneck. Compared to Poseidon 1. So I can't answer this directly. I can say that in RPO, the bottleneck is the inverse S-box, and in Poseidon 1, the bottleneck is the MDS multiplication.
Got it.
I
but
guess
in a
that
sense, they're
answered the
not
question.
super comparable, right? Because one has way fewer rounds than the other. Is that right?
Yeah, exactly.
Yeah.
Sure, but
Yeah.
I get you still compare them on performance, I guess.
Right. Okay. Well, if there's no more questions, let's thank Tomer and move to Leo, who will talk about Anemoy.
Yeah. Can you see my slides?
I think yes,
we can
but
see your screen, but
very
not the
big
slides.
lag. Last time there was a lag of about 10 seconds.
Well, I will see. Then I will just try to drop the pauses. Anyway, so yeah, Anemoy. So in this talk, I'm going to talk about two things, Anemoy and also a mode of operation we suggested alongside Anemoy called Jive. And I think both algorithms can hopefully contribute to the discussion about round skips. So first, Anemoy itself. So I'm unrolling the slide. We published it at Crypto. It's a joint work with a big team. Danny, who talked before, was a member of this team. And what we wanted to do with Anemoy, beyond just pushing the state of the art of the Conci slides. Is he the only one, or?
There's a delay of 40 seconds, unfortunately.
40? Ooch.
Yes.
Not sure what I can do.
If you send them to me, I might be able to share the slides instead. But I guess if you send them to me on Telegram, we can figure something out.
That's not going to be practical, I'm afraid.
Okay.
I'll quickly share. So now you can see my screen, okay? So is it okay now, or?
It's just taking a very long time to load. I think there's a massive delay. Why don't we move to Alan?
Okay.
And maybe you could restart your computer.
Yeah.
Cool.
Let's do that.
Alan, the floor is yours to talk about tip 5. Now it's better.
Actually, share my screen. How do I share my screen? Okay, then let's go. Floor is back to Leo.
Actually, I'm not sure. Okay, Leo, let's try real quick.
So I go, or
Yeah, sorry. It looked like the problem was fixed.
okay, let's try again. Sorry about that.
Sorry about the flip-flopping.
Yeah, the joys of remote presentations. Okay, so my screen.
Yes, that's better.
Can you see it?
Yes. Yes.
Okay. And now it's moving?
Now it's moving. Perfect.
Okay, perfect. Sorry about that. I'm not sure what happened, but who knows? If it's solved, it's solved. Anyway, so our goal with Anemoy was to first, well, mostly it was to push the state of the art on the design. We did this with two big contributions. One was a new S-box, which was an actual S-box, not just a monomial. And the second was to try to have a structure that is as close to what we usually do in F2. So it's built like some primitives that are defined over F2. So you have that your internal state can be seen as a rectangle, a two-dimensional rectangle with two rows. We have a diffusion layer, which is applied on each row in parallel. So it operates over half of the state. Each matrix operates over half of the state. Then we have a small linear layer over the columns, and then the S-box that's over the columns. So it's really a classical SPN structure where the S-box actually provides very strong mixing over its input space. The width of the state, so the length of the rows, you can choose it rather freely. And it has, again, this classical SPN structure where you have a kind of bit-sliced S-box and MDS layer. So the flystyle, our S-box, it's what's on the left part of the picture, and you have an inverse a monomial, which is the inverse of a low-degree monomial. So you have E, which is x to the power alpha, for a small alpha, and within the flystyle, you have its inverse. The Q functions are quadratic. And the key insight behind Anemoy is that you can use the open flystyle as the S-box of the cipher. It has a high degree, and it's a bijection. But during verification, you can look at the closed flystyle because there are CCZ equivalent, and I will not go over what that means. But it's a low-degree function. It's not a permutation, but we don't care. But crucially, it has a low degree, which is nice then for the verification. Anemoy has some known issues. So this is a picture I made for this workshop I gave a talk to last Sunday. You have variants of Anemoy. Each row corresponds to a variant. And then what you have in the other columns is the complexity of some attacks. So it comes from a paper on resultant-based attacks, which, as far as I know, is the best, at least as far as Anemoy is concerned, which was put on ePrint not that long ago. But what's interesting is that some versions are completely broken. So for instance, this version here, when the exponent is equal to 3 and you have just one column in your state, it's really insecure. The best attack is in 2 to the 80 instead of 2 to the 128. However, as you increase the state size, and when you use a smaller prime, it's what you do, then the number of the security level increases. So how did we choose the number of rounds? When L is larger, so when the length of the rows becomes larger, it's based on considerations related to regular cryptanalysis. In particular, we did not want to have fewer than 8 rounds because an SPN with fewer than 8 rounds seemed a bit iffy to us. But when L is smaller, well, for all of the values of L, but it became more important when L is smaller, we were using pointless estimates of the degree of regularity that are now completely outdated, but it was style at the time. We didn't, we're not the only ones who made this mistake, but it was a mistake. At this stage, the versions of Anemoy with a small L shouldn't be used. They are not safe. But when L is larger, they are not really affected. If you look at the version when L is equal to 10, you can have security levels that are in the 2 to the 200 for the 128-bit secure version. So the advantages of Anemoy, so when L is small, it doesn't have many, to be completely honest, because first, it's broken, and second, the native speed is going to be a disaster because of the huge exponents over large fields. But one of the key advantages of Anemoy is that you don't have round skips. Thanks to its real SPN structure, so the fact that you really have an S-box which completely mixes a small part of the state, you don't really have round skips. And for larger block sizes, it scales much better in terms of complexity because the MDS layer is only defined on half of the state. So if you have a state with 24 elements, you only need an MDS layer on 12 elements, which is going to help quite a bit. For performances, I had a look at what we had put in the paper. So it's slower than Poseidon. So you again have something like a factor 2. We were faster than ResQ Prime for this specific set of parameters because we have half as many inverse S boxes, basically. So that would be the reason, I think. For the constraints, these are some benchmarks that we made in the original paper for the case of Planck, but I don't think they're really relevant for us because it's here because it was for the case of large prime, small number of elements. So I will just skip. However, something else I wanted to talk about was the mode of operation if you want to build a compression function. So we introduced Jive in the case of Anemoy. And the reason why I think it's important is an observation on these round skips. So what do you need if you want to do some round skips? You want to have that diffusion is too slow. That's prevented by having an actually MDS linear layer. And you want, as an adversary, to have a lot of freedom in terms of how you can choose your input. And this can be solved at the mode level. So for instance, what we suggested was if you want to build a 2-to-1 permutation to use this mode, which we called Jive, or Jive 2 in this case, but it can be for any level of compression. And the key idea is that you make linear combinations of several inputs and several outputs of the permutation to obtain one output of the compression function. So if you have this more complex linear combination, in practice, you're going to be safer than just with a truncation or a feed forward because you will block these round skips. I think from a provable security standpoint, it doesn't change anything. But in practice, because of round skips, it can make a difference. So to conclude, if you have a small p and thus a large L, actually Anemoy isn't such a bad alternative to Poseidon. But I really think we need to talk about the modes of operations when we build compression functions. And that's going to be it for me. Thank you.
Thank you, Leo. One question I have is Anemoy going to be considered as part of the Athena consortium?
Very good question. I would like us to have at least a quick look. I will probably first have a look at, ask our industrial partners for some benchmarks to see if it's actually competitive. And then we will see. But okay, my initial, if you had asked me the question 2 days ago, I would have said, I don't think so. But since I prepared this talk, I realized that actually maybe we will see.
Okay, very nice. So Thomas is now one of the maintainers of Planck 3, and he can help with the benchmarks. And yeah, he's hoping to have many different hash functions implemented. Great. Next up, we have Alan, who will talk about tip 5, which I believe is used in production today.
Correct. Can you see my slides?
Yes.
And now still? Good. Yeah, this was a paper written in 2023 before we launched Neptune Cache. We launched Neptune Cache in 2025, February of 2025. So this hash function is live in production since more than a year. And before we had tip 5, we were using ResQ Prime optimized in a Stark VM, and we noticed that 80% of the time was spent hashing, and that was expensive. And so we decided to switch to a different hash function. And we all know that Blake 3 is the fastest, but you obviously don't want to use Blake 3 inside of a recursive Stark engine because Blake 3 doesn't arithmetize nearly as well as some of the alternatives. And so we thought, let's design one that arithmetizes well, but doesn't pay too much of a penalty in terms of CPU performance. And we were inspired by reinforced concrete, which beforehand I had tried to attack using algebraic methods, and I got exactly nowhere. because the split and lookup construction seems to thwart algebraic attacks. Now, reinforced concrete didn't seem like the best choice for our Stark engine at the time because it was tailored to large fields. And it doesn't have uniform rounds either. And so TIP5 takes that construction to in a different architecture. So we have uniform rounds, and we make use of a split and lookup tool. We use the Oxfoy field 2 to the 64 minus 2 to the 32 plus 1. Some people call this the Goldilocks prime. That's obviously wrong. The Goldilocks prime denotes a different number. We have uniform rounds that makes the description of the air simpler and concretely lower degree. And one more thing is, in contrast to the arithmetization-oriented hash functions that were available at the time, we knew that we needed a wide state and we knew that we needed a wide state, and that means that we can get away with fewer rounds. Specifically, in Neptune Cache, we target a security level of 160, and so our digests are 5 elements of this Oxfoy field. And so we want to be able to do 2-to-1 hashing using one invocation of the permutation. So yes, it is a sponge construction in overwrite mode. This confuses people sometimes. We don't add the input in between every permutation, but we overwrite the rate part. It's a substitution permutation network. So there's an MDS matrix, there's an injection of uniformly random constants, and there's a layer of S boxes, but the feature that sets apart TIP5 is that these S boxes come in 2 classes. There is a power map, x goes to x to the 7. Those are the T S boxes. And then there are split and lookup X boxes, which is essentially looking up into a table, and that table is defined in terms of this function, x goes to x to the 1 to the power 3 minus 1. And this function is defined over a different field. So it's embedding a foreign field arithmetic. You define this function over every byte of your field element, and then you end up with a new field element. So besides the split and lookup S box, we have the power map, and then the power map defends chiefly against statistical attacks, linear and differential cryptanalysis, whereas the S box attacks defends chiefly against algebraic attacks. So it's a hybrid construction. I'm aware of 2 papers that analyze TIP5, and they both present attacks that are more efficient than what was present in the original, than what was analyzed in the original paper. I think the current state of the art is that you can attack 4 out of 5 rounds with a small caveat, like you need to reduce the capacity by 1 element, and then you can attack it. But it's also worth noting that academically, an attack is any algorithm that breaks the hash function faster than brute force. And we are still targeting 160 bits of security. So academically speaking, an attack that works in 159 bits constitutes an attack, constitutes a full break of the cipher. But you could perfectly use that. If that were the optimal attack, you could perfectly use that in production. Back at the time, we had a back of the envelope benchmark against Poseidon. I don't think this was using the circulant MDS matrix, and so I expect the cost of Poseidon on the CPU would be a lot less. but still, TIP5 is pretty darn fast. It's not quite up there with Blake, but on par with Ketchak. But of course, that's the CPU cost. What we really care about, the main metric driving this research was how do we get the recursive proving as quick as possible. And by switching from RPO to TIP5, we ended up with a 2.68 performance improvement. And yeah, as I said at the start, Neptune Cache is live since February 2025. So this is another argument in favor of TIP5. There's a de facto huge bounty in terms of fame and perhaps even money if you can exploit it, if you can exploit a vulnerability in TIP5. That's it. Floor is open for questions.
Amazing. Any questions for Alan? I guess one question is, how much value is secured by TIP5?
I think the price now is 30 cents, and there are around 8 million coins in circulation. So that's what? Roughly 3 million US dollars.
Okay, got it. And the 4 out of 5 round skip, that sounds, like a lot to
It's not a skip, it's an attack.
Okay, got it. But it's not something that in practice you're worried about.
Let me put it this way. If I had been aware of the attack at the time that we were designing TIP5, we would have opted for 6 rounds instead. The original analysis in the paper concluded that you can attack 3 rounds, but 4 is difficult. And then those 2 papers basically proved us wrong.
Got it. Thomas asking, is it defined for other fields?
No, it is tailored to this field because this field has a particular structure that makes this particular split and lookup construction work. When you look up every byte of your field element, you have another field element. And generic fields don't satisfy that property.
Right. Okay. Cool. I mean, Kev asks a bit of a philosophical question. If we choose a new algebraic hash function, do we reset the cryptanalysis lindiness counter?
I don't know how to answer that question.
Yeah, I'm not completely sure how to interpret it either. In any case, thank you so much, Alan. This was very interesting, and look forward to the report from the Athena consortium as well. Next up, we have Marcus. You mentioned reinforced concrete, and I believe there's a couple other hash functions, skyscraper and monolith, that are in the same family. Marcus, the floor is yours.
Yeah, thanks. Hope you can hear me and also see the slides.
Yes.
Yeah, great. So yeah, this will be about monolith mainly as a potential alternative. So it can be like after TIP5, but the motivation is pretty similar. So essentially, we observed that high degree functions, like they're used in Rescue, for example, this the inverse function and so on, they are quite expensive and quite slow. So especially if the field is like not very, very small. But we also observed, and I mean that low degree functions, even in Poseidon, I mean, it's of course better to do like to the power of 7 or something, but still you have to do like full field multiplications and so on. So it's like still not very, very fast. So the idea behind like monolith was how can we minimize the CPU operations, in particular for the nonlinear operations. And we came to a similar conclusion as TIP5 here. We wanted to use this new technique of lookup tables in ZK. and then essentially also exploit those lookup tables, and in particular exploit the fact that many of those can be implemented with vector arithmetic on CPU, which again, of course, makes it much better. All right, so what are the main properties then of Monolith? So it has pretty good native performance, and in particular the lookup tables. So you don't actually have to use like lookups on the CPU. You can do the memory lookups without any, so you can do those functions without memory lookups to resist some sidechain attacks if they're of a concern to you. It also has an efficient proof system representation, but it's less efficient than, for example, Poseidon, particularly because we use the lookup argument, and we'll see some numbers also on that later. When we designed Monolith, we focused particularly on very small primes. So like then we focused on Fry-based proof systems, and like especially like 64-bit and 32-bit primes, or 31-bit primes. And there's some like constraints, which primes you can use and which primes you cannot use, or at least which primes are less efficient than others. But like for the Goldilocks or Baby Bear or M31 primes, it's fine, and it also works for some other classes of primes. And if you're interested in large primes, there's two new primitives, like there's reinforced concrete, there's also skyscraper. And I'd say skyscraper is better than reinforced concrete in almost every aspect, so should use that. But essentially, it's very similar to Monolith. Some things are different, of course, and it works only for larger primes. So it will not be the focus of this presentation. So yeah, how does Monolith look like? It has a very simple round function consisting of 3 layers, essentially. We call them bars, bricks, and concrete, and then it essentially does this like 6 times. So it's 6 round functions. Let me focus on the bars layer here. So it's like most interesting point of Monolith, or most interesting component. So the idea of that is that any input gets essentially, so any field input gets essentially split into smaller limbs. For example, 8-bit limbs or 16-bit limbs via this very simple sum here. And after the splitting, we apply some S-box on these limbs. It has to be chosen specifically for like some properties, but it's not so important. And the S-box looks like a SHA-tree lookup, essentially. And the advantage is that you can, via vector arithmetic, you can do many of those S-boxes in parallel. So you don't have to do it like specifically for each limb independently. And this provides strong algebraic security for a similar reason like Alan mentioned before, that essentially you are operating over a different field here. So you're mixing 2 fields, and then that gives you pretty high degree in the fields here. Yeah. So that's it. The bricks layer is very simple compared to the bars layer. It's just some Feistel-like construction where we have those squaring operations. Also, maybe the intuition behind that. The squaring is better than the cubic S-box, or the to the power 5 or 7 S-box in Poseidon in terms of constraints, but also compute. And doing this, but it's not a permutation in the prime field. So you have to use something like a Feistel construction or something to get the entire layer to be a permutation. So that's why we mix it with the Feistel-like construction. And particularly, it also has very good properties, even better than the cubic and to the power 7, but not like it's in the same ballpark. It's low degree, so it has good statistical properties. And yeah, it has to be mixed with some matrix or with some linear layer. And here we use a very simple MDS matrix. This is essentially exactly the same like it's done in the external rounds of Poseidon 1. It's just some matrix, some MDS matrix. And yeah, you can use different ones. You can circulant ones and all the newer stuff that came out recently. So about the performance, it's much better than Poseidon 1 or Poseidon 2. It's similar to TIP 5. It also comes very close to Ketchuk. And in the proving, however, we see that it's still better than Poseidon 2, but we see we have a problem. Well, not a problem, but it's like worse in the proof size, particularly because we need more witnesses due to the lookup argument here. So we essentially split each field element in each round into those limbs, and those limbs have to be stored somehow in the lookup in the trace table. And this, of course, needs some additional size. Security. So that's also very interesting why we're here, right? So 2 components, bricks and concrete, provide the statistical security, and this bars component is like field mixing provides the algebraic security. And to the best of my knowledge, there have been like 2 very nice papers that came out recently that analyze this type of constructions. Also, reinforced concrete, I think, was analyzed. or a particular skyscraper was analyzed, but also TIP5 and also Monolith. And currently, so Monolith still withstands these results, and in particular, the security margin remaining is still more than 30%. Now, if we think about something like round skipping, it means like this permutation has 6 rounds. If you can skip like 1 or 2 rounds, it's devastating compared to Poseidon. But I don't think that it's so easy here, because first we have a full MDS matrix, and secondly, particularly for the results in those papers, it seems very hard to bridge another round or even another 2 rounds, which would be needed for a full attack. And that's it from my side. Thanks.
Thank you so much. The performance is very impressive. My mental model here is that you're matching the plain text performance of SHA-3, and you're even faster than Poseidon 2 in circuit. So yeah, pretty amazing. Any questions from the audience? I guess one question I have is, are some of the attack strategies that have been applied to TIP5 potentially reusable in your context, or are they not at all?
Yes, so some of those are actually similar. So the problem was, so in particular for Monolith, well, it's not a problem. I mean, everyone knew about this. Is that the high degree S box potentially allows for nice differentials. You can avoid them pretty easily in Poseidon and stuff like that, where you have round low degree functions. But it's not so easy for Monolith. And these recent 2 papers show very nicely that you can exploit this low differential, even though it's like protected by the squaring functions. You can exploit this property and get through them, by doing something like which is called a rebound attack, where essentially attack from many directions. So yeah, reusable, for similar kinds of constructions, for sure. Yeah.
Okay, perfect. Thank you so much, Marcus. Next up, we have Stefano, who will talk about Arion.
Thank you. I will try to share my screen. All right, can you see it?
Yes.
All right, I will try to be as fast as I can. So I will be presenting Arion. It's an arithmetization-oriented hash function instantiated from the generalized triangular dynamical system, and it has been developed together with Arna Broj, Matthias Steiner, and recently also Luca Campa joined. And all right, I just want to quickly do a recap of the context. So most ZKP frameworks for verifiable computation operate over a large nowadays can be quite, there is a large range into what we mean by large. So it can be anything from 32 bits to 256 bits, but let's say a large finite field FQ. And algorithms can be represented as directed as a cyclic graph, which is a circuit, and if an arithmetic circuit or a Boolean circuit, right? And in general, the same algorithm, depending on the field into which we represent it, the circuit can have largely different sizes. And in general, we wanted to have a small size over the native field of the zero-knowledge framework. All right, so how do we construct then a cipher, for example, or a permutation or a hash function? Because usually the design strategies are quite similar. And the basic principle is like a product cipher, right? So we have a round permutation, and then we compound it together with a key scheduler. We get a compounded permutation, and this is the overall construction. So then the design basically boils down to how do we design the round function. Okay, typically the round function, the round permutation in turn is designed often as a structure which has a nonlinear layer followed by an affine layer. Sometimes the 2 layers can be interchanged. First you have the affine layer, then you have the nonlinear layer, but it does not really matter. So two famous examples are the substitution permutation network or the 2-branch or the Feistel network for the nonlinear part. And so it turns out that in 2010, Ostaph and Sperlinski introduced a kind of system of polynomials, which is called the triangular dynamical system. And this triangular dynamical system is in some way a generalization of several strategies that are used by typical designs of ciphers and permutation. And one nice property about these triangular dynamical systems is that it can exhibit degree growth anti-iteration with proper choices of the G and H functions, which implies low discrepancy. And in fact, they used it already back in 2010 to build up pseudo-random number generator. So in a work which is very related to Arion, which is the generalized triangular dynamical system by Arnold Roy and Matthias Steiner, this triangular dynamical system was extended into a generalized triangular dynamical system. The main difference is that in addition to the G and H functions, we have these permutation polynomials that are applied to the variables. And there are some constraints which require that Gi has no roots, which make the system invertible. And in fact, since Gi has no roots and Pi is a permutation polynomial, we can easily invert the triangular system, the generalized triangular system, by applying this formula. Yes. So just to see how this framework generalizes existing constructions, so we can see that we can obtain a full or a partial SPN just by canceling out the G and the H terms, or we can obtain a generalized Feistel by canceling out the P and G terms. And even more recent constructions, for example, this generalized Horst scheme that was proposed together with Griffin and the brick scheme that was proposed together with reinforced concrete, these kind of structures for the internal permutation can also be generalized by this generalized GTDS. Yeah, so what is Arion? Arion is an arithmetization-oriented hash function defined over prime fields, a prime field FQ, where the nonlinear layer, so it's a product cipher, and there is a matrix multiplication with a constant addition, so an affine transformation, and inside there is the nonlinear layer. And the nonlinear layer is an instance of the GTDS. And how did we select this instance? Well, we selected it in this way. So we have like that the permutation polynomial is a monomial, a low degree power map specifically, except for the last branch, because for the last branch, which was a high degree power map. And then the G and H functions are both quadratics, and in particular the G quadratic is irreducible, so since it's quadratic it has no zeros, and which allows for invertibility. And one key difference is that between like existing constructions which exploit these high degree power maps is that we choose D2 to have low Hamming weight, not necessary to be the same as D1. Because the thing is that in plain performance, let's say in plain execution, the evaluation of the inverse map is expensive regardless of how you choose the original value. So 1 over D is expensive to evaluate. And so this allows like a trade-off between the arithmetization complexity and the plain performance. And yes, so the other parameters are chosen such that everything is invertible. And about the security of the construction, so for statistical cryptanalysis, for this kind of constructions, especially over large fields, is not really that much of a threat. Well, you have lookup-based constructions, that is a bit of a different story, but for this kind of purely algebraic constructions, let's say differential cryptanalysis and linear cryptanalysis are not too much of a threat. And so we have very good bounds in terms of security. I forgot parentheses in the linear correlation, but yeah, that should be in parentheses. Algebraic cryptanalysis, however, is the most important threat in general for these arithmetization-oriented designs, and in particular for Arion. Okay, so interpolation attacks, we need a baseline number of rounds to prevent those, especially in the case one tries to do a meet-in-the-middle attack. And for the SICO constrained input, constrained output problem, which is especially relevant for sponge-based hash functions, the complexity of which generally depends on the quotient ring dimension. We have a bound which we computed and from which we derived the number of rounds. But then there was an attack, the free lunch attack, which showed that you can skip one round. And this attack is what actually dominates the cost when choosing the number of rounds. So we have a number of, these are like the round numbers. Our design originally was for the BLS 12 and BN 254 elliptic curves, scalar fields. And so we compare performance with other permutations. And just a note for the following the tables that will follow is that we adjusted some of the round numbers of the other constructions to match the attacks that were also applied to Arion. So let's say the cryptanalysis level was the same. It's not necessarily the most up-to-date, but it's on the same level. So for plain performance, these were the results that we obtained and over the BN254 scalar field. And interestingly, while Arion is like the other high degree constructions quite slower than Poseidon or Poseidon 2, it was still significantly faster than other inverse power map based constructions like Anemoy, Griffin, or Rescue Prime, at least in this setting. And for Planck arithmetization, additionally, our Arion was, for medium and large sized instances, was the best, required the lowest number of Planck constraints, Planck gates, except for like 2 to 1, there it was the second best, Griffin was a bit better. And for R1CS arithmetization, we're not quite as good, but we're still very competitive. We're still in the same range as the other constructions. So NMO is the best in R1CS, Griffin is also competitive, and Poseidon is a bit worse, so we're basically in the same ballpark as Poseidon. And for air arithmetization, here is where like a construction like Rescue Prime shine, but Arion even here is still very good. It's the second best for medium and large sizes permutation. These are compression rates, so basically large size permutations. So in conclusion, Arion is a hash function based on the generalized triangular dynamical system, whose security derives from the generic cryptanalysis that was done on this construction, but it has been refined. And it offers plane performance which is better than other high-degree designs and a lower arithmetization cost across different techniques. So this can actually be a good thing if you want to integrate systems which use different arithmetization techniques. They use the same hash function. So maybe it's very expensive in one, for example, I think about lookup-based techniques, right? If you have a framework which has lookup support and another one which does not have it, then the cost will explode. So we have lower arithmetization costs across different techniques. And further consideration, just I want to point out that there have been these compression modes like trunk and jive, which achieve better efficiency than sponge, but these are not randomorically differentiable, and cryptanalysis can be different. And so we recently proposed a mode which is called PAX that unifies and generalizes both the sponge and compression modes, and is appearing soon in Usenix. Thanks for your attention. If you have any questions, I will be glad to answer.
Thank you so much, Stefano. We're way over time, so we're going to move on. But any questions, feel free to ask in the chat. We have 2 final presentations, including one which is unpublished, called BenX. That will be the very last presentation. Congrats to the 50 or so people who made it so far, 2.5 hours in. So Sundas, the floor is yours, and then we'll have Fabian.
Thank you. I'm sharing my slides. Can you see now?
It's loading, but it should load. Yes, we can see it. Yes.
Okay. So today I will talk about the XH. I did this work with Omar, Ahmed, Al, Muhammad, and Leo. It is available on ePrint, and just this week we received the acceptance news from Journal Design Codes and Cryptography. Let me briefly outline the structure of this presentation. First, I will start with the motivation, where I explain the idea behind this work. Then I will give the design overview. After that, I will discuss the stage size and security. Finally, we'll present some benchmarks. The motivation for XH is to combine the marvelous strategy with a new type of S-box. These S-boxes are based on exponentiation over an extension field, which allows us to apply the nonlinear layer to a vector of field elements rather than processing each element individually. We explore 2 versions of XH and implement them over both Goldilocks and M31. From this construction, we propose 4 concrete hash functions. 2 are optimized for zero-knowledge stars named XH12 Goldilocks and XH8 Goldilocks, and the other 2 are optimized for circle stars named XH24 M31 and XH X#16M31. These two versions can easily be adapted to koala bear. Here you can see the first variant of X-hash. Let me explain how it works. First we have, I can show pointer, yeah. First we have an F step. It starts with the round constant injection, followed by an MDS multiplication, and then a non-linear layer where we apply a power map X alpha to each state element. Next, we have the B step, which is start by the MDS multiplication and then the round constant injection. And then again, we have a non-linear layer, but this time we use the compositional inverse power map. After that, we have a P3 step, which is basically on the exponential extension field. And here we first did the round constant injection, and then the nonlinear power map is the cubic extension field, which maps the state element again back to the base field. So at the end of all these three steps, we have a last step where we did an MDS multiplication, and then we added the round constants. So based on this design, we construct two instances, X#12 Goldilocks and X#24M31. And here the choice of alpha depends on the field. So for the Goldilocks, it's 7, and for the M31, it's 5. On this slide, you can see the optimized version of X-hash design. So the key idea here is to use the partial layers of the compositional inverse S-box. Means instead of applying the non-linear layer to the entire state, we apply it to a subset of elements, which improves efficiency. So based on this design, we construct two optimized variants named X#8 Goldilocks and X#16M31. So here I will summarize the design part. First, regarding the state size, Goldilocks-based construction uses 12 state elements with rate 8 and capacity 4, while the M31-based construction used 24 state elements with rate 16 and capacity 8. So in X#8 Goldilocks, the compositional inverse power map is applied to 8 out of the 12 state elements, and in X#16M31, it is applied like the compositional inverse power map applied to 16 out of 24 state elements. In terms of security, Goldilocks-based construction provides 128-bit security, and the M31 construction provides 124-bit security. Finally, all four proposed hash functions consist of 6 rounds. Since I have no idea about the implementation, however, Alkindi from the Midden team help us with the benchmarking in Plonky using Plonky 3. On Apple Silicon, we see that X-hash is about 2 times slower for Goldilocks, but when adapted to smaller fields, they offer better performance. Here you can see the comparison in case of Goldilocks for R1CS, Plonk, and air representation. And the most efficient hash function in each representation is highlighted in bold font. And in this slide, all of you can see the performance comparison in 3 representation in the case of M31 field. And same the highlighted efficient one, hash function one is highlighted in bold font. Thank you.
Thank you so much. Great presentation. Any questions for Sundas? I guess one question I have is, as I understand, you're currently working full-time on hash functions as part of your PhD. Are you looking to design even more hash functions, or are you kind of happy with X-hash?
Yes, I am currently working on the design part of the function. Actually, I am currently working on designing a new hash function. Hopefully soon you will see that design. And also I'm focusing on the cryptanalysis of Poseidon. So I'm working on that too.
Okay, very exciting. Looking forward to the new hash function.
Yeah, thank you.
Final talk of the day from Fabian. He will talk about BenX, a very new and unpublished hash function.
All right, thank you. I hope you can hear me and see my slides.
Yes.
Okay, perfect. So yeah, thanks for having me and presenting BenX, which is a joint work with a lot of people you've heard of already today, like El or Marcus or Stefano, and also others like Thomas, Luca, and Arnab. And yeah, so let's get right into it. Why do we need a new hash function? I mean, this question is a bit hard to answer, I would assume, but our starting point at least was that one of our partners worked actually on specific hardware for cryptography. And there was a realization that we have usually these huge areas reserved for the number theoretic transform in there. And then we have a huge area also reserved for hash functions in there. And then maybe the main idea was to use kind of the structure of the entity or kind of larger entity blocks to then build kind of a hash function out of it. However, along the line of working on this project, we actually realized that the performance gains that we saw were interesting in their own merit, also for kind of application outside of purely hardware. All right, so let's dive into the core building block, which is the Benesh network that we use to build up our hash function, which is essentially kind of like a butterfly construction we may have seen in Anemoy or in other designs. We essentially have two branches, two input values that basically are used to produce two output values, and all of them are fed into four different functions. And this is kind of the core building block. However, of course, when designing a hash function, by designing a permutation first, we want each building block to be invertible. So, of course, we had to first find a way to make these individual functions together produce an invertible full building block. And quite generally, we state the following way. Of course, I haven't updated the numbers here to be zero indexed as to the right in the image. But essentially, if both functions on the left branch are the same, and then the difference between the two functions on the other branch are a permutation, then the whole resulting network is a permutation over the two values, essentially. This is a generic method for all primes, but to be a bit more precise, we, of course, looked a bit at the concrete primes that most of us are interested here. And then also thanks to Remco for saving this slide and arguing why this is still called Goldilocks. Yes, indeed, we looked into Koala Bear, Mersenne, Goldilocks, and Baby Bear, but this construction and the approach that I presented before, and this, of course, much more detailed in the paper, works for any prime really to create a permutation. So what does this mean? We have a lot of complex permutations in there, polynomials that need to be evaluated. However, if we look more closely at it, we see that we have kind of these common degrees. And we know that F0, F1 belong to the same branch, and F2 and F3 belong to the same branch. So for example, this value x to the 5 means the right branch always only needs exactly this exponentiation. This intermediate steps here will also be interesting because when you produce the value x to the power of 7, very often you will anyways produce these intermediate powers. So you can evaluate this polynomial with actually very little overhead when it comes to arithmetization also. All right. So now we've talked about the nonlinear building block, really. And of course, this is not enough. We need to, of course, also mix the entire state because we're not working over state size of 2. So in a simplified form, our construction could look like this. Of course, it has up to 8, 12, 16, 24 element states. But this kind of propagates as you would expect. So what's happening is that we have a pairwise application of these Benesh networks. And then we need to think about the concrete matrix or concrete linear layer rather that we want to have there. And we've gone through a couple of different possibilities where we looked at just having cyclic rotation as is used in a generic Benes construction. We've also looked at, of course, non-MDS matrices as they are seen in Poseidon, but of course this whole call here is also about the weaknesses that these non-MDS matrices introduce. And of course, we know that MDS matrices alone are costly. Of course, the idea is, I think, somewhat akin to what we see also in Anemoy, that we essentially have an S-box that is applied on two elements of the state, which allows us also to split the MDS matrices on these parts of the state. So how we frame this is to look at the output vector of such a computation as a vector of extension field elements or quadratic extension field elements, where we essentially can shrink the state vector to half the size, where each element now is a polynomial of degree 1, essentially. And then we can apply the same MDS matrix to this vector in the extension field to get an output again in the extension field, which can then be reinterpreted again into the regular state size, where if you only look at the implementation of things, it's important to note that this reinterpretation and interpretation in the first place don't actually cost anything. This is more of a mathematically conceptual representation, really. So what we have implementation-wise, again, is really the individual matrix application onto the even and the odd elements in our state vector. And this means that our dimensions of the matrix are halved. So in total, this shrinks the matrix to a fourth the size, which makes essentially finding good MDS matrices a lot easier. And that's also something that we've heard in a couple of talks before, that a lot of the cost in the plane performance comes from evaluating these MDS matrices and then finding, for example, low Hamming weight MDS matrices or circulant MDS matrices that can be evaluated with the Fourier transformation. These tricks are all, of course, much easier if our MDS matrix is smaller. All right, while still, of course, retaining the nice MDS properties, having the high branch number. All right, so now to some instances. Of course, the instance, kind of the final product of a long cryptanalysis, is now in the caveat that this is, and this is a great team we're having, but of course, this is only internal cryptanalysis as of now. So we are really looking forward to having outside eyes looking onto it. However, of course, to the best of our knowledge, we try to integrate especially all the new findings and all of these constructions to really have a comfortable security margin and arrived at the following round numbers that you can see at the very right of this table here for the different primes. The slight differences in round numbers are mostly due to also having a higher degree in some of the primes. All right, so now getting to the evaluation of the hash function. We've evaluated everything in Plonky-free and used for that exactly the parameters as the different hash functions are implemented in there. So when some hash functions are not implemented in some settings, this was due to them not being present at the time of coding this. Of course, I'm also happy to include more in the table in the future. So what we're really seeing here is that BenX in the plane performance positions itself as, I would say, on par with Poseidon in some settings. I think in Koala Bear, we're really close. In Baby Bear, Poseidon 2 has a bit of a head start, so to say. But in the Mersenne and Goldilocks field, we are actually faster than Poseidon 2, where only Monolith is faster. However, of course, Monolith applies the split and lookup strategy, and this may just not be available in all proof systems and settings. So this is definitely something where BenX can also be an interesting choice. Comparing to Poseidon 1, if we want to move away from Poseidon 2 altogether, then we see that across all prime fields, we actually have the superior performance. And one important thing to note also, it's not provided in Plonky-free, but also the assumption would be that our MDS matrix actually increases in benefit for the larger state sizes. So for the sponge construction, where we use a state size of 24, we actually expect the advantage against monolith of this linear layer to be somewhat larger and to be either on par or even better for some of these primes if implemented. All right, so now let's look at the proof system comparison. We've also evaluated this in Plonky-free, where for the sake of fair comparison, we really just implemented what was already there with exactly the parameters provided, and then also implemented our construction with the same set of parameters. And I think we have kind of a nuanced view on this. I think Koala Bear is also chosen in a way because of the nice performance for Poseidon. And I think this is due to Poseidon having the degree 3 power map there. And we see we can only get around half the throughput for our proofs with a slightly larger proofs. And however, for Baby Bear and Goldilocks, we see that actually our proof of throughput is much, much higher, which is, of course, I think it's a bit, in essence, the situation is the following. In Baby Bear and Goldilocks, you have a degree 7 power map in Poseidon, which is the same degree as our S-box. And when doing the constraints efficiently, you can essentially use exactly one constraint per branch in the S-box, which is exactly the same number of constraints that you would have in a full layer of Poseidon. So already with 8 full rounds in Poseidon 2, this would equate almost the entire constraints already that we have for our S-boxes. And then there's the partial layers on top of that. So I think that kind of explains the significant difference that we're seeing here. All right, I think that was a quick way throughout the paper, skipping a lot of details, of course. I hope I could still convince you that this is some interesting project that we're having here. Fundamentally, we have a design that's built towards hardware sharing, where we can really reuse these data paths of this high-radix entity, achieving higher area efficiency. Then
thank you so much, Fabian. We're a little bit over time here, but looking forward to the publication. That's going to be on ePrint, right?
It's going to be on ePrint next week and then submitted as well.
Okay, amazing. Thank you so much for Fabian for doing this final presentation, and thanks to everyone here who has endured 2 hours and 45 minutes. Bye, and see you next time.